So our aim is to solve the Klein-Gordon equation, the quantized Klein-Gordon equation, on FRW spacetimes. Remember, we proved that we will succeed with an ansatz of this general form. And so we tried that in the case of cosmology as well. So that equation star expresses the field as a function of space and time in terms of creation and annihilation operators that take care of the commutation relations, and mode functions that take care of the equations of motion. Remember also that we use here the usual commutation relations between the A and A dagger. And our general formalism tells us that the key difficulty will be to find mode functions uk of x and t, which are not only solutions to the Klein-Gordon equation, that's a given that they have to be, but also they must be normalized in the sense that they obey this so-called Wronskian condition. This condition being the condition that translates the commutation relations between phi and pi into the commutation relations between A and A dagger. You can also view this as a normalization condition for the mode functions, because if you take any mode function, and this is a solution to the Klein-Gordon equation, any multiple of it will also be a solution to the Klein-Gordon equation, but this fixes the overall normalization of the mode functions because it's not linear in U, right? If a set of U's is obeying that equation, 5 times those U's is not. Okay, and we also know already that these mode functions are not going to be unique. There's going to be many of them that obey that, and we'll have to find out which set is the right one. Okay, so the strategy will be to find such mode functions, and then we can build the Hilbert space representation of our field phi hat of x and t. Namely, we use the A and the A dagger operators to build a Fock basis. We start with a vector that's annihilated by all of the AK, and then we apply the A dagger case arbitrarily many times on that vector 0 here. And by suitable normalization, we obtain an orthonormal basis here. That will give us a Hilbert space representation of our phi and pi for all x and t. So that's all fine, but again, the mode functions are not unique. We could choose a different set of mode functions, a different set of classical solutions U tilde now, which obey the Wronskian condition here, and are solutions, of course, of the Klein-Gordon equation. And in principle, in a generic curved space-time, there is no reason to prefer a priori the U mode functions over the U tilde mode functions. There's no canonical choice in general. And by generic, I mean a generic curved spacetime that doesn't have killing vector fields, that has no particular symmetries. In this case, there's really no way of telling which solution would be preferred. Remember that in principle, mathematically, even physically, you can use both. It's a matter of convenience which ones you choose. We also know from the math of it that when we choose a different set of mode functions, and correspondingly a different set of A and A dagger operators, then we're still describing the same quantum field. It's because of the Stolnford-Norman theorem that we know that this field, the field expressed in this way, is the same as the field expressed with the other mode functions and the other A and A dagger operators, we know from that theorem that the Fock bases generated by the A tilde and A tilde dagger operators must be just a unitary transformation away from the Fock bases generated by the untilted A and A dagger operators. So by choosing two sets of mode functions, the U's and the U tildes, we generate two sets of basis vectors in the very same Hilbert space. And of course, two bases of the Hilbert space are always related by unitary transformation. So now let's apply that to cosmology. So for convenience, we reformulated the equation of motion such that it's no longer an equation of motion for phi, but instead for the auxiliary degree of freedom chi. It's just another variable. It's the rescaled version of phi. In this way, we got rid of the friction term in the equation of motion, in the Klein-Gordon equation. And we found that the Klein-Gordon equation, expressed in terms of chi, takes this shape. Second time derivative, where this is the conformal time, x is the co-moving positions. Second time derivative, and then the sum of the second space derivatives in the co-moving coordinate system, plus this more complicated now mass term is equal to 0. Notice that it's not just the regular mass term here, but there's also this extra term here, and that is really encoding all of the non-trivial action because of the expansion of space-time. See, we could consider a massless field, for example, in which case that term would be absent. So this a squared is not really the key to encoding the expansion of space-time. It's this term here. Now this is a partial differential equation in which both space and time derivatives occur. So in particular, if we dropped that term, then we would simply have, for every x, a harmonic oscillator. A harmonic oscillator with a time-dependent backdriving force, right? So if this space derivative is absent, then for every x we no longer have any space derivatives in this case. So for every x we have a differential equation in eta. Second time derivative in eta is equal to something or other times eta, that's the harmonic oscillator, and the backdriving force constant is no longer a constant. It's this function here. So we have a time-dependent harmonic oscillator, and the opening of the harmonic oscillator parabola is given by that prefactor here. And something that will be very important is that this can be positive or negative, depending on the relative sizes of those two terms. And that means that if we drop that term, you might have here a harmonic oscillator that is either this way or, in fact, that way. And when the harmonic oscillator is this way, then of course we expect runaway solutions. We expect that the phi field will grow out of bounds. Not the phi, the chi field will grow out of bounds. That doesn't mean that the physical field phi will grow out of bounds. Because the physical field phi is chi divided by a, the scale factor, which itself is blowing up, right? So, but in terms of the chi, we should expect both possibilities, a regular harmonic oscillator or an inverted harmonic oscillator. In the case of the inverted harmonic oscillator, there is no particle picture, because the spectrum is going to be continuous, not discrete, like for this harmonic oscillator. Okay, now that was just to anticipate what will come up. for now, one thing at a time. This term is present, and therefore the different harmonic oscillators at different locations x are coupled to another. And of course, we can fix this by doing a Fourier transform. So under Fourier transform, the d by dxi operators become I times ki. And so we do a spatial Fourier transform here. And remember, this is a Fourier transform in the co-moving coordinate system. In the coordinate system which is expanding along with the space-time. So we do what we did already for Minkowski space. We do a Fourier transform in order to turn this partial differential equation that has both time and space derivatives into a bunch of uncoupled ordinary differential equations that have only time derivatives. So the definition is the usual definition of a Fourier transform. The chi field is originally dependent on time and conformal time and co-moving position. We Fourier transform in the spatial directions only, not in time, just in space. And then we obtain the Fourier transformed field chi hat of k and eta. And I should say that it's a tradition in this field of research that for some reason or another, we don't write here chi hat of eta comma k, which would be logical, because before Fourier transforming, we write eta comma x positions, right? So after Fourier transforming that variable, that should become a k here, but that's not how it is done. Usually one writes a subscript k over here, but it means exactly the same thing. Perhaps because it's convenient when we put everything in a box and these are discrete, then this becomes more like a label. With an infrared regularization, the momentum vectors have discrete components, of course. Okay, and that is the inverse Fourier transform. And analogously, we define the Fourier transform for the canonically conjugate momentum field with exactly the same formulas. So, in terms of the Fourier transform field, the Klein-Gordon equation therefore takes this form. Second time derivative plus, and this used to be the Laplacian, second space derivatives is not just a k squared, and then here we have this time-dependent mass term. And you see how the k squared combines with those pre-existing terms. So what we will have to consider now is when is this positive, when is that negative? Under which circumstances is it positive, under which circumstances is negative? Because that decides about the fate of the harmonic oscillators that we are now considering. Now we are no longer considering at every point in space a harmonic oscillator. No, those guys were coupled because of the Laplacian. Now we are considering again at every point in momentum space, at every point in co-moving momentum space, we have a harmonic oscillator. And that harmonic oscillator has a time-dependent backdriving force. But very important is that they are uncoupled harmonic oscillators. And that's, of course, because we used a co-moving coordinate system. The wavelengths really grow, but they grow exactly the same way that the space is growing, that space-time is growing. And so if you use a coordinate system that grows along with the space-time, then the wavelength stays exactly the same in that coordinate system. And the fact that the wavelength stays the same under time evolution is the statement that the harmonic oscillators are uncoupled. Every wavelength has its harmonic oscillator. If you excite a harmonic oscillator with a particular wavelength, if you excite the harmonic oscillator of a particular wavelength, of a particular mode, then it will keep oscillating, but it will not trigger shorter or wafer. It will not trigger shorter or longer wavelength. Not in the co-moving coordinate system. Okay. Now, keep in mind too that this formula would be the same for a classical field expanding that lives on an expanding space-time. If you have a classical complex valued scalar field that evolves on the background of an expanding space-time, that would be its equation of motion. And therefore, we can really work with intuition here as well. After all, the mode functions will have to be number-valued solutions to the Klein-Gordon equation. The mode functions will be almost classical in their interpretation. Okay, so what we have here is for every co-moving momentum, we have a mode oscillator, and its frequency is given by the square root of this. So we write it like this: second time derivative, conformal time derivative, plus frequency squared times chi equal to 0, where the frequency squared is this whole thing, so therefore the frequency is this. And the key is that this can go negative, in which case the frequency is no longer real. It's imaginary. And what that means is that oscillations become growth or shrinkage. Now, part of this behavior, I think, ought to be very plausible. At least part of it. See, if you have why is the frequency time dependent? Well, remember that for waves, such as electromagnetic waves, there is a relationship between the spatial wavelength and the wavelength in time. If you know the spatial wavelength of an electromagnetic wave, you can calculate how often it is oscillating, how frequent, what the frequency of its oscillation is, its temporal frequency. Right? So if you have an electromagnetic wave of very short wavelength, it's going to be oscillating very fast. The temporal frequency is very fast too. And if you have an electromagnetic wave of long wavelength, let's say on the radio dial, you take medium waves or long waves. They not only have a long wavelength, they also have a slow oscillation frequency in time. And of course, it's just, k naught squared minus k vector squared equal to 0. Just the masslessness of photons that dictates that, the relationship between the frequency of oscillation in time and the spatial wavelength. Now, we have waves. We are dealing here with waves whose wavelength is really increasing. Because space is expanding, wavelengths get stretched. So therefore, we should expect that as the wavelength is changing, the frequency of oscillation will change. What this is telling us is that it's a highly non-trivial thing. How the frequency of oscillation changes when the wavelength is changing. I mean, that it should change is clear, but how exactly it does change is given by that formula here. And as I said, it's even classically the case. You could just take a classical wave and see how it behaves under expansion. For example, you could take water waves and then somehow model the expansion of the water by, I don't know, having a flux from underneath or something, and then see how the waves propagate on that expanding surface. And you should see something like that. So in extreme circumstances, the frequency of these mode oscillators may become imaginary, and that is if A double prime is large enough. Right? That's what we need. This is positive. Mass is positive. Mass squared in particular is positive. A squared is positive. The only situation where that frequency could go imaginary is when this becomes large. right? So A double prime got to be large for that. So what that means is that the universe has got to be accelerating. It's got to get faster for that purpose. So for example, if it's just coasting, if it's expanding, but not in an accelerated way, then, I mean, in the sense of A prime being equal to, A prime being constant, but A double prime being 0, that would not be able to cause that thing to go negative. So we need that the acceleration is rapid enough, but rapid not in the sense of speed, but in the sense of acceleration. Another thing that we can read off already is that the discussion of the two cases of is the oscillation going to be, is it still oscillating or is it no longer oscillating? Is omega still real or is omega imaginary? That discussion will depend on the value of k. What we can already tell from looking at this equation is that for sufficiently large k, this is always going to be positive. Right? Only if k is small enough can this thing go negative. And the physics of this is that for sufficiently large k, which is to say for sufficiently small wavelengths, for sufficiently small wavelengths, you will always find that the mode is oscillating ordinarily in time. The intuition behind it is that expansion is like curvature between space and time. And when you have a wavelength that's very short, then you're looking at wavelengths that are short compared to the curvature in question. So you don't see the curvature just yet. It will be a general feature, as we will see later in this course, that for sufficiently large k, for sufficiently small wavelengths, therefore, we get back to the usual basically Minkowski space behavior. And then only when the wavelength becomes of the order of where the gravity becomes important, that's where the physics becomes very different from Minkowski space and the expansion becomes important. Okay, so now I leave it to you as an exercise to show the following simple things, namely that the hermeticity properties of the chi field are such that chi dagger is chi of minus k. You prove that just like you prove it for any real valued function. Any real valued function after Fourier transform has this property. So any self-adjoint operator valued function after Fourier transform also has that property. And the same is true for the canonically conjugate momentum field. It's just a property of the Fourier transform that comes out. Also, check the canonical commutation relations. It's a little subtle. The canonical commutation relations between chi k and pi k prime are not the usual ones with k minus k prime, but instead with k plus k prime. So remember, by construction, the chi and its canonically conjugate pi are really having the usual commutation relations as long as x is concerned. As long as you write them in the position space, by construction, they are canonically conjugate pairs. But when you do the Fourier transform, then this happens that chi with pi has this with a plus here. Now, you can get a minus here simply by putting a dagger there, right? If you put a dagger here, then you are here. You see, if you put a dagger there, it's a minus k down there. So they will have the chi has the usual commutation relations with the pi dagger, which is to say that they are the canonical pair. Phi is canonically conjugate to pi dagger if you write everything in momentum space. Just have to be cautious about this. It's an easy source of mistakes. All right, so we make this ansatz as usual. namely that the chi field can be written as mode functions times annihilation and creation operators. Traditionally, one puts a 1 over square root of 2 here because then later the formulas for the V and V star will have as factor of square root of 2 fewer. Okay, so what are then what's the relationship between the mode functions u that we had to express phi and the mode functions v that we have to express chi? So let me just show you where we started. We started with this. The phi is expressed in terms of these mode functions, and the chi is expressed in terms of the mode functions v. All right? So that should be easy. I'll leave it to you as an exercise to relate the two to each other. There's a Fourier transform in between the uk of eta and x and the vk of eta, and there's also a rescaling by a factor of a. It's all very straightforward, but it's good to write it down. Okay, so now the proposition is that this ansatz will work. It solves the hermiticity condition right away by construction, simply because if you take the dagger of this, take the dagger of that, then you automatically get what you ought to, which is this, that you get the chi with a minus k. Okay, so you take the Hermitian conjugates, then this term becomes that term, except that k flips to minus k. And you see that? It's important that you have here the k's, and here you have the minus k. That's important so that when you take the Hermitian conjugate of the whole thing, you get itself back, except that this term becomes that, that becomes that, except for k going to minus k, as we should have because of the Fourier transform. Again, easy source of error if you forget that this is the case. Okay, and it's clear that if the vk solve the Klein-Gordon equation, then so will the chi k, because the creation and annihilation operators are, of course, time independent. So that's just a statement that the mode functions have to obey the Klein-Gordon equation. Here it is again. And remember, there were three conditions: the hermiticity condition, the equation of motion, but also the commutation relations between the phi and pi have to arise from the commutation relations between the a and a dagger, and that leads to the Wronskian condition. And in our case, this is the Wronskian condition, which is much simpler than what you've seen before, where we had this infinite sum and all those things. Now, with the Fourier transform, we've already decoupled all of that, and we now have simply to obey this condition here. And I leave it to you to show that this is what became of the Wronskian condition. You can prove this in two ways. You can either take the general Wronskian condition and prove that in the special case of FRW spacetimes, it reduces to this with our choice of coordinates, etc. Or you forget about the general things that we proved, and you just prove it for that particular case. You just write down the condition that the phi and the pi obey the proper commutation relations, and then ask, what condition do the v's have to obey such that the a and a dagger have the usual commutation relations? And then that's what you get. Also, you may want to check something that we proved in all generality previously, but now we have a special case where you can prove it directly without appealing to any complicated theorems. Assume that the Wronskian condition holds at one point in time. Show that it will hold for all times. Remember that this is equivalent to saying that the time evolution is unitary, which is equivalent to saying that the commutation relations are conserved. Remember that preservation of the commutation relations is the Noether conservation law corresponding to the unitary symmetry of the quantum theory. And how do you prove that? Well, you just take the derivative of this and use the equation of motion. Try it out. See, if you differentiate that, you get, I'm telling you the whole solution here. You get v prime here, v prime there, that goes away. But you also get a term with second derivatives. But the terms with the second derivatives, you can express using the equations of motion. And then see if that works out. So show that the Wronskian is conserved. Okay, so the conclusion so far is this. In order to obtain the solution to our quantum field theory on a curved expanding space-time background, we do this. We find for each mode k a mode function solution. That is a solution to the classical harmonic oscillator with time-dependent frequency. Then we make sure that the mode function obeys the Wronskian condition. If need be, multiplying with a constant, because remember that the Wronskian condition is sort of a normalization condition. And once we have that, once we have for every mode its mode function, then we can use the associated A and Dagger operators to build our Fock basis, and we know it's an orthonormal basis of the Hilbert space, and we are ready to go, can calculate whatever we want. However, and that's going to be very important, how shall we choose our mode functions? Remember that there's an ambiguity in this. For each choice, let's say the choice of the Vk or the choice of the V tilde k, we obtain by Stone von Neumann the same quantum field. But the basis, the Hilbert basis that we get, the Fock basis that we get, the A generated by the A daggers that came with the V, or generated by the A tilde daggers that came with the V tilde, those two Hilbert bases are not going to be the same. In principle, not a problem. We can choose any one of them to calculate whatever we want. But we also need to be able to make contact between our math and our physics. And for that, it will be very convenient, it will be sort of necessary that we can pinpoint which vector in the Hilbert space describes the no particle state. You see, when I talked about these states so far, I never talked about them as one particle or two particle or no particle states. I mean, not today anyway, right? Let's just view them as Fock basis vectors. We know that these may not be one particle, two particle states at all. In particular, if this is a one particle state, that's probably not a one particle state, because they are related by complicated unitary transformations. So it would, however, be very useful, and it will be extremely important, to be able to pinpoint which vector in the Hilbert space describes the no particle state. And then, with a little luck, and we will be so lucky, then that state that we pinpoint in the Hilbert space as being the no particle state, that state we can arrange to be this state here. In other words, if you find the right state in the Hilbert space, which describes no particles, then your ambition should be to find those mode functions, V, which come with A and A dagger operators such that the A operators annihilate the vector that we determined is the vacuum state. So that we then can say, aha, this is the vacuum state, and therefore this is going to be the one particle states, the two particle states, etc., the whole logic there. And then we would say, yeah, okay, this is the vacuum state, this is one, this is two particle states, so these are not vacuum and one and two particle states, and so on. So once we can identify which vector is the vacuum state, our ambition is going to be to choose the mode functions such that the associated A operators annihilate that vacuum state, because then we can build up all the n particle states from that. What will be very difficult, what will be a task that we will have to face then, is that which vector in the Hilbert space is the vacuum state will depend on time. At early times, this might be a different vector than at late times, or at even later times. And so we may have to work with different ones of those spaces, with different mode functions because of that reason. So how does that come about? In the Heisenberg picture, the state vectors of a system, such as this quantum field theory, is always the same Hilbert space vector. Right? So if you prepare a system in a particular state, then by construction, it's always going to be in that state. It's that vector in a Hilbert space, that's the state the system is in, and all of the evolution is put on the operators. Only the operators evolve in time. The state of the system is frozen by construction. Nothing can change that, not even curvature of space and time. The Heisenberg picture means the state is frozen. And the operators involved. But that's the key to understand what I just said about the vacuum state. You see, the observables evolve in time. The position operators or the momentum operators, the angular momentum operators, if you talk first quantization, they change in time. And if you have observables that change in time, what that means is that, for example, their spectrum can change, their eigenfunctions can change, because these operators are dynamical. They change over time. And what that means also is that if you take one observable, for example, and you follow its time evolution, and let's say you're interested in its third eigenvalue. Let's say it has a discrete spectrum, and it's bounded from below, and you're interested in the third eigenvalue. Then the third eigenvalue will have an eigenvector. That eigenvector depends on time now, right? Because the observable depends on time, its eigenvalues depend on time, its eigenvectors depend on time, right? And therefore, you have a time dependence of eigenvectors. Now consider the Hamiltonian. That's one of those cases. The Hamiltonian, let's say, has a discrete spectrum, and the third eigenvalue might depend on time. The third eigenfunction of the Hamiltonian depends on time. At every different point in time, it's a different vector in Hilbert space. Just a sec. The ground state of the Hamiltonian too. Ground state of the Hamiltonian can depend on time. And in the simplest case, we will later find that it's actually more complicated than that in curved space-time. But if you look at, for example, the ground state of the Hamiltonian, it can change in time. And if that were the vacuum, it would mean that a different state is the vacuum at different points in time. So the state of the system, the state that the system is in, is always frozen in the Heisenberg picture that we use here. But the meaning of the Hilbert space vectors can change in time, because the Hilbert space vector's meaning is given by the observables, and the observables are changing over time. Guillaume.
So we are working the Heisenberg picture.
Yeah.
So, okay. It's just because you were saying the operators change in time and the states change in time. So
no. That's what I wanted to say. Yeah. But you see, this is the subtle thing. I think you just came a little late. So the thing is this, that only the operators change in time. The state is frozen, right? The state that it is in. But because the operators change in time, the meaning of the vectors in Hilbert space changes. So in particular, if the Hamiltonian changes in time, then no wonder that the ground state of the Hamiltonian changes in time, right? And so also we shouldn't be surprised that which state is the vacuum state can depend on time. Even though state that the system is in is frozen. If you ask which state is the vacuum state, or which state is the third eigenstate of the Hamiltonian as a function of time, right? It is a function of time because the Hamiltonian is a function of time. Okay? So we are not used to thinking in the Heisenberg picture much, but this is just the Heisenberg picture. It's nothing special about quantum field theory. It's just the Heisenberg picture which has the observables evolve in time and therefore the interpretation that they carry. Yeah?
If there's like really slow change with time, isn't there the adiabatic?
Yes, there is. Yes, that's right. That's right, and that will concern us a lot. There's a difference between adiabatic evolution and non-adiabatic evolution. Yeah, it's, you know, when the observables change very quickly in time, if the Hamiltonian, for example, changes very quickly in time, then the system might get excited, or if you change the Hamiltonian very slowly, then the system does not get excited. Now, in the Heisenberg picture, this is a little difficult to talk about because the way that we usually talk about this is obviously Schrödinger picture, where we say that, you know, the vector in the state that the system is in changes over time, either adiabatically or non-adiabatically. But in this case, it's a property of the observables, not of the states. So we'll do that carefully with the adiabaticity. The state is, of course, always the same in the Heisenberg picture. It's the observables that then evolve non-adiabatically. But you can still see exactly how the adiabaticity or non-adiabaticity comes in by looking at the Heisenberg picture in the quantum field theory at the mode functions. See, the mode functions evolve in time, and they capture the dynamics of the observables, such as phi or pi. And as the mode functions are evolving in time, they may do so adiabatically or non-adiabatically, in ways that are very similar to what you know from first quantization. Okay, so the bottom line is, in Heisenberg picture, the state vector that the system is in is frozen by construction. However, the observables and their operators evolve in time, and therefore the meanings of all Hilbert space vectors changes over time. In particular, you know, the identification of which vector in the Hilbert space is currently the vacuum state that can change over time if the Hamiltonian is time dependent. So that means that we may, for example, choose a set of mode functions whose associated vector 0, meaning this set of mode functions comes with A and A dagger operators, such that the A operator annihilates this one. We can choose such mode functions such that at a particular time this vector happens to be what we identified to be the vacuum state by some other argument. That would be a reasonable choice to make. We could say, let's say at time t equal 5 minutes, we find out that in the Hilbert space, this particular vector is the vacuum vector, the no particles vector. Then we could go into our calculations and look at all possible sets of mode functions, and we pick out that set of mode functions, which has the property that if we now apply its A operators on the state that we identify to be the vacuum, we will find it annihilates them. And that would be a very convenient choice of mode functions, because then we can immediately also tell what the 1 and n particle states are. But which vector in the Hilbert space represents the vacuum can change over time. So later on, at time t equal 20 minutes, it's a different Hilbert space vector that has the distinction of describing the no particle state. Then we can go back to the drawing board and we can say, all right, we need new mode functions. So we identify mode functions, let's call them V tilde, which come with A and A dagger operators with tildes on them. And we choose them such that the A tilde operator is annihilating the state 0 tilde, which is the one, by construction, that we identified as being the vacuum state and no particle state at time t equal 20 minutes. So now we have two sets of mode functions in the game, two creation and annihilation operators in the game. And there's going to be a Bogoliubov transformation between the mode functions, between the A and A daggers, and so on. And so in particular, if at early times the system was actually in that vacuum state, then we can tell from this business that at a later time it will not be in the vacuum state. And we need the Bogoliubov transformation between the two Hilbert bases to figure out exactly how many particles have been produced. So how many possible choices are there of mode functions? Well, we can write down mode functions v, v tilde, v double tilde, and so on. It turns out there are infinitely many choices, as we proved earlier on in the abstract. Now let's look at this concretely. Let us consider each mode separately. Of course, you could have Bogoliubov transformations that even mix the modes. If you think about the Dabur diagonalization, you can mix the boxes. I give you an exercise to calculate also exactly what happens when you do that. But in this case, let us just not mix the boxes. Let us just look at one case. Let us consider one mode each mode individually. So we take one mode oscillator, one of those harmonic oscillators for 1K. Then here is the harmonic oscillator equation. That's what the mode function has to obey. How many solutions are there of this? Now, in principle, it's a two complex dimensional space of solutions, right? Because we have up to second derivative. Therefore, by the general theory of differential equations, we expect that the solution space of this linear differential equation is two-dimensional, in fact, two complex dimensions. Because our mode functions are allowed to be complex valued, two complex dimensions, that is 4 real dimensions. So the mode, we can pick any mode function here out of a 4 real dimensional space, two complex dimensions. If V is a solution of the Klein-Gordon equation, if Vk is a solution to this Klein-Gordon equation, then Vk star is also a solution to the Klein-Gordon equation because there is no imaginary unit in this. The coefficients are real, therefore if V is a solution, V star is a solution. And V and V star will span this two-dimensional solution space as long as V is neither real nor imaginary nor, it has to be a mixture. It has to have a real and an imaginary component. Okay, so we can use V and V star to form a basis in the solution space. But since our solution space has only two dimensions, two complex dimensions, any other solution to that Klein-Gordon equation has to be a linear combination of these two. That's important information here. If V is a complex valued solution to the Klein-Gordon equation, V star is as well. The two of them together span the two-dimensional solution space, and therefore any other mode function that we may consider is going to be a linear combination of these two basis vectors with coefficients alpha k and beta k. And that plays out for every single mode. We have this Bogoliubov transformation between the mode functions. Now it turns out that the actual dimensionality is 3. You see, the solution space has 4 real dimensions, as we said, but one real dimension is lost because the solutions have to obey also the Wronskian condition. You see, you can't just use any solution to the Klein-Gordon equation, it also has to obey that condition. And it is a complex equation, and you might think, doesn't that kill these two variables, two dimensions? After all, it's a complex equation. No, it does not, because this equation really just says that the imaginary part of V prime V star is equal to 1. It doesn't speak about the real part of it. You see, because this is something minus its complex conjugate. So therefore, it's just it's an equation about the imaginary part only of that product. So it's just one real equation. So that takes one dimension away. So we've reduced it now to 3. But it's not a 3-dimensional vector space anymore, because this is not a linear condition. So what we have is a 3-dimensional submanifold of a 4-dimensional solution space. For 4-dimensional vector space of solutions, we now have a 3-dimensional submanifold of that. So here's a proposition. Let's assume that Vk is a complex valued solution to the Klein-Gordon equation that also obeys the Wronskian condition. Then the V tilde, an arbitrary V tilde, which is, as we already argued, always a linear combination of V and V star, will also obey the Wronskian condition and therefore will be eligible to be used for the purpose of quantization if the coefficients alpha k and beta k obey that famous relation here. Okay, so remember, the Bogoliubov transformation isn't just relating solution of the Klein-Gordon equation to solution to the Klein-Gordon equation. No, they also have to be solutions to the Wronskian condition, right? So if V is a solution to the Klein-Gordon equation, V star automatically is 2. But you also need that the alpha and beta coefficients obey that, so that if this is a solution to the Wronskian condition, this is also a solution to the Wronskian condition. So in order to go from one eligible set of mode functions to another eligible set of mode functions for quantization, you need that the linear combination is not arbitrary, but obeys that condition. Easy to prove. It's good to do it though, so I leave it to you as an exercise. So what we obtain then is that the chi field in momentum space can be written equivalently, either as expressed in terms of the V's and the V stars and their A and A dagger operators, or completely equivalently, we can write the chi field also in terms of the V tildes with the A tilde and A tilde dagger operators. And similarly, we can go to any number of other representations. We just have to choose coefficients alpha and beta that obey that condition, and then we can produce any number of new bases, new ways of writing the same field. Any such transformation from one choice of mode functions with operators, with raising-lowering operators, to some other, and the associated Hilbert basis to some other choice is always called a Bogoliubov transformation. So clearly, if you have a Bogoliubov transformation from a first set to a second set, and then from a second to a third, there's also a Bogoliubov transformation from the first to the third. Okay, so we have 2 tasks now. First, we need to make those Bogoliubov Hilbert basis transforms explicit, because we will need them. We will have explicit Hilbert basis pairs, and we will need to calculate how the one basis is expressed in terms of the other. And we will have to find out how to make our choice of mode functions. In other words, we'll have to find out how to identify, how to pinpoint at any given time which vector in the Hilbert space currently denotes the vacuum state. So that's just math, but this will require some physics here, some intuition. So let's do the Bogoliubov transformations. Bogoliubov transformations of Hilbert bases. The question is, how can we express the basis vectors of one choice of mode functions as linear combinations of the basis vectors obtained with another choice of mode functions? the proposition is that if we put together the equations B and P, let me show you. If we put together these two equations, namely how the V tildes are linear combinations of the V and the V star, and the fact that you obtain the same field whether you write it this way or that way. See, you just plug in this into that, basically. If you do this, you find that the relationship between the A's and the A tildes is this. But just by plugging the B into the P and then comparing coefficients, we obtain that the A operators are a linear combination of the A operators plus A tilde operators plus the A tilde Dagger operators. This is quite different from what we had before with the harmonic oscillators that were driven by an external force, where we had that we also had two sets of A and A Dagger operators before the driving and after the driving. And in that case, they were related. A was related to A tilde, or A in was related to A out, by being equal plus a constant, this J naught, if you remember, right? And what we were able to conclude from this was that what starts out as the ground state ends up being a coherent state. Because a coherent state is an eigenvector to the annihilation operator, right? And so similarly, we expect that we should be able to tell something about the nature of the states that we get from this new transformation law here. So indeed what we find now is that the condition of the vacuum I shouldn't say really vacuum, but if we consider the condition that defines the vector 0 for one choice of mode functions, namely the vector that's annihilated by the A operators of one choice of mode functions, if we consider that condition, we can now rewrite that using that transformation rule, that Bogoliubov transformation. And what does it become? Well, we just replace the AK by that whole bunch. And so we obtain that this acting on that vector is vanishing. So what we have to solve is this equation here. Ultimately, what we want is an expression for the vector 0 that comes with one choice of mode function in terms of the Fock basis of the other choice of mode functions. If we can do that, then we can relate all the basis vectors to another, right? Because once we can express this vector in terms of the Fock basis of the other Fock basis, then we simply apply, in order to describe the vector A dagger acting on that, in terms of the other Hilbert basis, we just express the A dagger then using this, and so it all follows automatically then. So in order to find out the map from the Fock basis of one choice of mode functions to the Fock basis of another choice of mode functions, really the key thing is to express that vector in terms of the other Fock basis. Now we could derive that over a page or two, or I just give you the solution and we check that it's true. And here's the solution, and then we can check why that is true. So we wonder, how is that a linear combination of the other Fock basis, of the tilted Fock basis? Well, here it is. If we make this ansatz, it will succeed. So the idea is that we write this as an expression in terms of A tilde dagger operators acting on the 0 tilde 0 vector. And when you go with that ansatz into it, this is what you obtain. So the vector 0 that comes with the mode functions without a tilde is this expression acting on the mode function, on the vector 0 tilde that comes with the mode functions with a tilde. So it's a product of all those exponentials, which you could also write, of course, as the exponential of the sum, or integer, it doesn't matter. This is just a normalization factor that is needed to show that this is normalized. And what are these things doing here? So depending on how the two mode functions are related to each other, the two sets of mode functions are related to each other, and that relationship is, of course, given by the alphas and the betas. Given how they are related to each other, so I mean, we are assuming that we know the alphas and the betas, alpha-beta coefficients. We can now express that vector in terms of all those higher Fock basis vectors. Now, an important thing that, I mean, we will get into more detail into what all of that means, but one thing that we can already read off from this is that, first of all, if the transformations do not involve a beta, if the beta is 0, and we could have that, see, remember, this is the Bogoliubov transformation that we are talking about. This is the most general transformation. It's the most general choice. That's the most general change of bases in the Hilbert space of solutions. If we make our change of basis in such a way that we choose the beta coefficients to be equal to 0, which is certainly something we can choose. We just have to choose our alphas to be of modulus 1 in this case. If we choose the betas to vanish, then we obtain a trivial Bogoliubov transformation. Because if beta is vanishing, then that whole exponent here is vanishing, and then you see that this vector is just proportional to that vector there. And also remember that all the alphas have to have modulus 1 in this case, so that's just 1, so this vector doesn't change. If, however, beta is not 0, if our Bogoliubov transformation is truly mixing the V's and the V stars, if, therefore, the A and A daggers are truly mixed, you see that comes up in here, if the beta is not vanishing, then the A is a linear combination of both the A tilde and the A tilde dagger. In this case, the vector 0 really does change, and it changes in an intriguing way. Namely, what we then obtain is always even powers of A daggers acting on that state. And they always act in such a way that you have a K and a minus K. Let's think of this exponential as being spelled out. It's a 1, and then the next term is minus this, and the next term is 1/2 this squared, and then so on. It's an exponential that you can write as an exponential series. And the lowest order term is just 1, so that's just nothing. It's just the trivial term here. But then the next contribution is going to be A tilde dagger K and A tilde dagger minus K acting on that, which if, just hypothetically, if we are in the situation where currently this is the vacuum state, then that tells us that this is actually a state that has a component which is a two-particle state. Because two particles are being created here out of the vacuum, and one particle shooting off in the K direction and another particle shooting off in the minus K direction. And then the higher order terms produce more pairs of that kind. So you can view this as indicating that if particles are being produced in this way, or whenever particles are being produced in this way, because the beta coefficients are not zero, then they're being pair produced. They're being pair produced with opposite momenta. And that has led to the picture that you may have heard of, that basically the production of particles here is that virtual particle-antiparticle pairs are ripped apart from each other. They would normally just fluctuate and then recollapse, but because space-time is expanding, you might have those pairs ripped apart. I think it's overselling the case if you want to interpret it literally, just a sec, literally in this way. But this is the origin of it. Keep in mind that for a real-valued scalar field, as what we are considering here, even though the mode functions are complex values, remember that the Klein-Gordon field was a real-valued one. After quantization, it was self-adjoint operator-valued one. For those particles are the same as antiparticles, so you can maintain that interpretation. And then if you extend the study to fields where you have different particles and antiparticles, such as charged fields, spinors, and so on, then you actually get the pair creation of particles and antiparticles in this way. Guillaume?
Yeah, I mean, this expression, you create pairs of particles in momentum space, so where, there's always this hockey picture of these particles popping out from a certain point.
Yeah.
But that's maybe part of the misconception.
Yes.
Localized things.
Yeah, exactly. I wanted to tell you that this is where the picture comes from, but I would like to caution you not to try to develop too much of intuition with it, because it's very much a limited intuition. You have to keep in mind, in particular, and this may be the most important argument why you have to be careful with this pair production process. It's very treacherous to think that particles would be produced at the horizon of a black hole. And the reason is that if you look at the at the typical Hawking photons, it turns out that their wavelength is typically the size of the black hole. Right? So it's very difficult to say that they came from the horizon for that reason. Right? You're over-localizing them then. Okay, so this is a proposition, namely that is true. And how do you prove this? Well, what you have to prove is simply that this equation holds. Right? What you have to prove is that this is true. Right? This vector is defined as the vector that's annihilated by A. The claim is that this vector is this. Well, let's check it. We apply A to it. We apply A to it by applying this to it, because A is this. And that is in terms of the tilted quantities. That whole mess here is also in the tilted quantities. So all you have to do is apply this operator on that bunch and use the commutation relations between the A tildes and the A tilde daggers, and that's all you have to do. Now, it may look daunting to do this, to move, the A tilde dagger, you can easily move through this because the A tilde daggers commute with the A tilde daggers. But this thing is going to non-trivially commute through those things. So you have to write this as a series, and then in each term you have to commute the A tilde tediously through all the powers of the A daggers. When you do that eventually, and eventually you collect all the terms that you have, you will find that it comes out right. But what you will find very useful is to first prove this. Namely that when you have A times e to the power of lambda times A dagger, then it is given by this. Just prove this first, and then you will find that the rest comes much more easily. The reason why that is true is easy to see once you realize that the commutation relations between A and A dagger are exactly the same commutation relations as those between the derivative and the multiplication operator. Right? If you take d by dx, x minus x d by dx, then I'm claiming that this is 1. Why? Well, just apply that to f of x, and you will find that this is f of x. Right? And so it's no wonder that when you commute the a through this function of a dagger, you obtain the derivative here. Right? And so that's how that works. Right? So this is to say that dx f of x, comma, in this sense, interpreted in that sense, is equal to f prime of x. You can prove this from that, the Leibniz rule. And if you just, once you prove that, right, if you just replace the d by dx with a and the x with a dagger, same thing. Totally same thing. I mean, the cleanest is you just prove it term by term. Just spell it out what it is, prove it, and then you go about doing it for this as well. Now you might think, wait a moment. I have second powers of a dagger up here, not first power of a dagger. Why are you giving me this simple thing here and you have to do the more complicated? You don't. It is single power of a dagger. Because that has a different index as that. Right? So as far as the commutation relation, if you have an a tilde k here, it will get hung up only with the k, not with the minus k1. For that purpose, the other thing is just a constant, and so you can work with this. Okay, so I really hope some of you, all of you, do these exercises because it's so important. Okay, so equation T, this one, the transformation. Oh, by the way, yeah, so this, I'm claiming, tells us everything about the Bogoliubov transformation from one Fock basis to the other. Because, well, yeah, initially, it just tells us how the zero vector is represented in terms of the tilted Fock basis. But from that, you can immediately tell also how the what would be the, for example, one particle states, the a dagger k on that is represented in terms of the tildes. And the reason is that you can express the a dagger k in terms of the tilted quantities, namely using this. Just take the dagger of the whole thing, and then you take the dagger of that and apply it to this, and you immediately have the answer. It's just application of the a and a dagger operators on that. So you just have to use commutation relations. There's no further guesswork involved in this. So any arbitrary Fock state here can be expressed by applying a dagger operators on that, which translates into applying corresponding powers of the dagger of this on that. So we really have the complete Bogoliubov transformation from the one Hilbert basis to the other. So then what's the interpretation of this transformation law? This one, the big one? Well, let's assume that, for example, this vector and that vector are those Hilbert space vectors which happen to be the vacuum states at times eta 1 and eta 2. Let's say, because of physical arguments that we will get into later on, we will have identified that. We will have found that this happens to be the Hilbert space vector, which is the vacuum state at times eta 1, and that one describes the vacuum state at time eta 2. Then let's assume that at the first time the system state is prepared to be the vacuum state. Then what that means is that we should choose the first set of mode functions, namely the vacuum state is then that vector 0. At the later time eta 2, the vacuum state is a different state, but of course our system is still in the old state, this one. And even though the vacuum state is actually the 0 tilde vector later on, the actual state of our system is this one. And in this case, we can immediately tell what was going on. Namely, see, this is the state that describes, this is the state that at the earlier time was the vacuum state. And let's say we prepared the system at that earlier time in the vacuum state. So this is, even at the later time, this is still the state of the system. Even though it's no longer the vacuum state, it's still the state of the system, because by construction, in the Heisenberg picture, it can't help it. Cannot move. But at a later time, this vector is the vacuum state. And therefore, this whole vector is going to be a linear combination of the vacuum state, of the two-particle state, four-particle states, and so on. But this whole vector is the state in which the system is in, which means that, in this case, particles have been produced. Because the state that the system is in is this one, which is to say it is this one, but at the later time, this is an excited state, because this is the ground state. All right, so this is the structure of how particle creation will come about. But of course, we will have to go way beyond that in various ways. First, we will not only consider the case where we can even talk about particles. We will have situations where the harmonic oscillator in question will go this way. And then there's no particle picture. And what we will find then is that the beta coefficients still make sense. No longer do they mean then particle production. They then mean something about the size of the quantum fluctuations of the field. We will calculate by how much the phi field or the chi field, how much does it fluctuate about its zero value, about its expectation value. The expectation value of the field will stay zero. But the fluctuations around it are time dependent. And we will find that beta is crucial for describing how the standard deviation, how the size of the quantum fluctuations depend on time. So the field picture, in the sense of amplitudes of fields, will survive, even in the case when the harmonic oscillators are inverted, whereas the particle picture will not survive. And then secondly, of course, we will have to go beyond this picture by quantizing also the metric, at least small perturbations of the metric. Yeah?
So this operator is like a squeezing operator.
Yes, it is.
In quantum optics.
Yeah.
And if we had a coherent state initially, then the coherent state gets multi-mode squeezed. But from our intuition, from just quantum mechanics, we know when we have a coherent state and we squeeze it, then the x and the p values, the one stretches and one compresses. So is that going to give us behavior? Say we have expanding space-time, then if I have a certain, coherent state of photon, then it's going to get stretched out with time.
Yes. Remember that the vacuum state is already a coherent state because it's eigenvector to eigenvalue 0 of the annihilation operator. So we have that situation that we are transforming a coherent state into a squeeze state, or remember that squeeze state and coherent states are really the same thing. It depends on the perspective, what you consider the primary harmonic oscillator. But really what's going on is, of course, that the fluctuations in one variable can get larger when in the canonically conjugated variable they get smaller. We will come back to that issue because it has been argued that this squeezing has to do with the emergence of classicality. This is something that we will discuss later on, namely, how is it that those quantum fluctuations that arise in quantum field theory and curved spacetime and that are large in both wavelength and amplitude, how is it that those quantum fluctuations became classical fluctuations that we can now see as classical temperature fluctuations in the sky? When and where and how did the measurement take place? At what point did it go from quantum to classical? And it's not really settled, that issue, but one school of thought is that it has to do with extreme squeezing and getting essentially a classical degree of freedom out of that. Basically because one variable becomes very strongly squeezed and the other one becomes very small, basically undetectable, which means you can trace over it, and the pure state becomes a mixed state, and that would give you the transition. But there are other views too, and we will discuss it when it arises.
So when our potential flips and this kind of like particle picture that we're used to no longer really makes sense, what would happen if we had some detector at that kind of energy gap? And could we, in that kind of formalism, when we want to say a particle is what a detector detects?
Yeah, actually, for a while now, I've been looking for a student to look into that. Yeah, very interesting. And also communication between detectors in this case. Yeah, very interesting, yes. I don't quite know what to expect. But as a project for this course, you know, yeah, you can pursue that if you want. But remember that I'm asking you to do something similar, which is, you know, find out what the quantum fluctuations do for Minkowski space. That's already a nice project. But then also try, let's see how far you can get with expanding space-times. And then, of course, if you manage to do that, the key thing is to see what happens with the quantum fluctuations when the potential flips. How does that show up in the quantum fluctuations in their spatial and temporal distribution? Yeah, and then to put a detector there, well, yes. Right, we are done for today.